section. The time should be 2:21, so we'll get started. Our first speaker is Marco Festa-Bianchet from the University of Sherbrooke. Marco did his PhD with Val Geist at the University of Calgary, and for the last 16 years, he's been the chair of the Mountain Ungulate Specialist Group with IUCN. So Marco, take it away.
Thank you, Mark. Okay, I assume everybody can see my screen.
Yes, we sure can.
That is a yes. Okay, well, thanks for the introduction, Mark, and thanks to everybody for listening. So I've been working on various species of mountain ungulate for the last 40 years, and with some luck, see if of course, when I tried, it went to the next slide. Now it's refusing. Sorry, this worked when we tried, and it's not working now. Let me try something else. No. Okay, I'm gonna stop. Try again.
I have a copy of your presentation if you need it.
Well, it worked just now. It's there. I'm just not sure why it's not. Let's try this one. Yeah, no, but look, Mark, can you put yours on? Because otherwise just going to use up all my time here. I can see on my other screen, but can you? Great. Now oh, now I'm seeing the presentation, but I've lost the Zoom.
Mine's opening.
Okay, I'll just go.
Sometimes the Zoom will like minimize into a little bar that just goes along the bottom that you just need to expand up, or you can hit the Zoom logo along the bottom as well.
No, I found it. Yeah, no, I'm back home. But I cannot see the presentation. I'll try sharing once again. Okay, can you see it?
Yeah, we're seeing your presentation, just not in presentation mode.
Okay, now let's see. Okay, it worked. Great. Okay, so what I was trying to say, I spent about the last 40 years working on various species of mountain ungulate. Most of my work is on monitoring marked individuals. Today, I'll first go over quickly some of the main evidence that intense selective hunting will lead to evolution. And then I'll spend most of the time presenting a critique of two recent papers that conclude that for a management scale, hunting-induced evolution is irrelevant, and I'll try to convince you that actually what you can conclude from those two papers is that under some circumstances, it's actually quite important. So first, let's look at what are the conditions that we need so that selective hunting will lead to evolution. Obviously, a targeted trait has to have strong heritability, and we know that horn size in ungulate is about 30–40% heritable. But then you need very intense selective harvest, and you need to do that over many decades. If you want to be very effective, you let the selective pressure coming in early in life so that you remove, for example, large horn rams before they can breed. You have to do it consistently over a large area, because otherwise you might have immigrants from, say, protected area that will weaken the selection. And if those immigrants exist, you should shoot them. Now, this pretty much describes the way bighorn sheep are managed in Alberta. If you look at the list, you can also see that this is quite easy to fix. If, for example, your harvest is made up of mostly rams that are age 8 years and older, those rams would have bred. It's unlikely to have an evolutionary effect. The other point that is very important is that under some circumstances, this is extremely strong selection. So, for example, in the mountain population with a 40% rate of harvest of legal ram, a ram that became legal by 40 years of age had an 8% chance of surviving to rat at age 7. If a ram did not become legal until age 8, he had the 60% chance to rut at age 7. So this is a substantial selective pressure, which compares favorably with what we do with domestic animals. So the picture on the right, you have half of a skeleton on the left of what merino domestic sheep look like when they were brought into Australia about 110 years ago. And on the right is what they look like now. So persistent directional selection will get you substantial evolution. And not surprisingly, this is what was shown in the Ram Mountain data. This is the main result from Pigeon et al. The blue line is the phenotypic decrease. So over these 25 years of study, horn size decreased substantially. Most of that decrease was phenotypic. It mostly had to do with an increase in population density. What's important here is the orange line. This is actually the genetic decline during this time when the population was subject to unlimited harvest of 4/5 curl rams. And these genetic values are calculated using a pedigree, same way you would do it for a domestic animal. The dotted line here represents 1996. And at that point, the hunting regulation were changed so that after 1996, the harvest pressure was much lower. You can see that the orange line stopped declining. It didn't actually recover. This was not a significant change, but the hunting-induced evolutionary change stopped when selective pressure was weaker. Now, this is only one population. If you want to take this to a broader scale, you can use the harvest data. And as we've seen in a number of presentations today, several of the jurisdictions have very long-term data, which is great, particularly the ones that collect the measure annuli of the rams that are shot. Now, these data are useful, but they're biased. And you need to take into account those biases. First of all, if your hunting regulations are based on a definition of minimum horn size, minimum curl size, small rams cannot be shot. So if the ram is illegal, it will not show up in your sample. If the ram is legal, the age at which it will be shot is correlated with its growth rate. So a ram that has rapidly growing horns will be harvested as a 4 to 5 year old. A ram with slow growing horns will be harvested at late age. And you need to take this into account when you analyze harvest data, otherwise you end up with spurious conclusions, and you will see in a moment. Taking into account those biases, what is the evidence that ram horn size is declining? Well, it's declining in Alberta, and the best evidence is the distribution of, the age distribution in the harvest. Here you have the proportion of the annual harvest of bighorn rams in Alberta made up of rams aged 4 to 5 years. And you can see that in the 70s, early 80s, and early 90s, it typically accounted for a fifth, and in some years up to a third of the harvest. And then you can see this nice decline over 40 years, so that now it's typically less than 10%. The reason why this proportion of 4 and 5 year old has declined in the harvest is not because the hunting regulations have changed, is because these young rams are no longer legal because horn growth has slowed. This graph also shows you where you have an initial problem, because if, as in these earlier years, up to a third of your harvest is made up of rams that are essentially too young to really participate in breeding, that is exactly what you want if you want to cause an evolutionary change. Hunting regulations in Alberta are pretty uniform. Another way of looking at harvest data would be to compare areas that have different hunting pressure. We have done that for stone sheep. This is work by Duhard et al. And for stone sheep in northern British Columbia, Mathieu Duhard compared an area, the piece with very high levels of harvest, the black dots in the figure, and an area with a much lower level of harvest, the Skeena. And the lower harvest was essentially because the access is much more difficult. You can see that in the Skeena, this is a flat line. So over these 25 years of data collection, there was no significant trend in horn size. In the area with a high hunting pressure, we see a decline, again, at the order of maybe 2, 3, maybe 4 centimeters. So these results are important because they show that trophy hunting is perfectly sustainable from an evolutionary viewpoint if you have a lower harvest rate. So to recap what I told you so far, we have genetic evidence based on a pedigree of harvest-induced evolution from one population in Alberta, and harvest-based evidence from bighorn sheep in Alberta and stone sheep in British Columbia. Now, these results have been criticized, and one critique was this modeling approach, which was commissioned by the Journal of Wildlife Management to show that evolutionary change as a consequence of selective harvest is really not much of a concern. So the model prediction, as they were shown in the original publication, are here on the right, and you can see that applying harvest rate of from 1/4 to 100% of legal rams, the model does predict an evolutionary decline, but over a time scale of 100 generation of bighorn sheep is a little over 700 years, not really relevant for management. Now, this model had 4 errors, all of which contributed to the result that it concluded that evolution is not important. One of these errors was that it used arbitrary values for genetic and phenotypic variance. So this is really the basis of the model, and the input of how much variance is there in horn size and how much of it is related to genetics were essentially made up, which is surprising because values for additive and phenotypic variance of bighorn sheep were available in the refereed literature. Now, I had some issues with the editorial that accompanied this special issue, so I sent a letter to the journal, which was published, and in a rebuttal, the editors of the journal and some of the authors involved actually provided the model prediction when they actually used published value for bighorn sheep, additive variance, and phenotypic variance. So what you have here on the right is the original publication that you've already seen. On the left, you have the predictions of the model when you use published value for phenotypic and additive variance with 25% of harvest of legal ram. You may notice that the slope looks identical. That is because the y-axis scale was changed. In reality, the slope is double. So when not changing anything else in the model, but using values that are appropriate for bighorn sheep, the model prediction doubles from a decline of about 7 centimeters over 100 generation to a decline of about 15 centimeters with 25%, 15 centimeters with 25% of legal ram harvest. Now, you may notice that there are some other differences other than the fact that the scale was changed between these two figures. And one of the obvious differences is that the harvest at a level of 50, 75, and 100%, which was in the initial publication, has now disappeared. Well, in a paper that Michael Morrissey has produced and for now is still unpublished, we used the code for the model, which was publicly available, which is very nice, and applied those higher harvest rate. Now, I'm showing this over only 10 generations to provide something that is more relevant to management. Typically, we're starting to get information in the order of 2.5 to 6 generation of bighorn sheep, about 7 years. The red line is the observation of genetic decline that was observed at Ram Mountain. So the red line are actual data. And you see that if you apply a 50 or 75% harvest rate to this model, you get a result that is very similar to what we actually saw for Ram Mountain. So this, my first take-home message is that when you fit it with parameters that are adequate for bighorn sheep, this model that claimed to demonstrate that hunter-induced evolution is weak predicts pretty strong evolutionary change, actually what we found at Ram Mountain. So we have support from this empirical study, support now from a modeling study. What would be a reasonable next step? Well, it would be very interesting to do a much broader analysis of harvest data where we compare what are the consequences of different management schemes, ideally accounting for weather effects that we know affect horn growth. It'd be nice to account for density as well, but unfortunately that information is rarely available. And this is what Lashar et al. Did in this paper that was published last year on evolutionary application. And they concluded that in 78% of what they call hunt units, there's no problem. So not only was the conclusion that really evolutionary change in horn size is not something that we need to worry about this was taken up a lot in sort of hunting magazines and podcasts to show that really this is not a problem. Now, if you just compare the pie chart for Alberta up here with what I produce here, which is a summary of all the American jurisdiction, you'll see that there is a bit of a difference in that the proportion of units that are decreasing is much greater in Alberta than in the States. And I remind you that in most of the American jurisdictions, the harvest is much more conservative. Now, there were two problems with the Lashar paper. The first one is that they ignore the fact that shot rams are not a random sample of the population, and so they use data from harvested rams to adjust horn size at 7 years of age. I do not have the time to show you why that is a problem, but clearly you can imagine that if you're a young ram, you're only going to get shot if you have very highly developed horns, and the consequence of this bias is also that a time series is much less likely to pick up a decline, as we have shown in a number of publications. I'm going to concentrate on what they use as a definition of stable. And their definition of stable is that there was no statistical significance. Now, that clearly is dependent on sample size. The more you split up, say, a jurisdiction into smaller hunt units, the smaller your sample size of harvested rams within each hunt unit, and the less likely you're going to be able to pick up a significant decline. So let's ignore significance for a while, and let's just look at what the trends are like in different jurisdictions. So now I've colored in red any decreasing trend, and in blue, any increasing trend, regardless of statistical significance. There was actually one population in the state, or one hunt unit, that was actually stable. It really didn't change over the time series. You can see that we go from the Lashar et al. Conclusion that there was no decline in 78% to only 38% that are now increasing or stable. And in Alberta, the few that are increasing tend to be the ones where the definition of legal rams was switched from 4/5 to full curl. So obviously over time, you're going to see an increase if the regulation legislate that you can only take bigger rams. Now, obviously, this is not a very justifiable approach, because some of these declines, even though the trend is negative, may be very weak. They may not mean very much. It does suggest that there's difference between Alberta and the American jurisdiction, but what you need is a proper statistical analysis. And the proper statistical analysis in this case would be to use a mixed model estimate, essentially a meta-analysis, which seeks to determine what is the proportion of hunt units where horn size is likely to be declining once you account for all the available data. And Michael Morrissey and some co-authors did in a paper that we just resubmitted to Evolution application. And we did it separately for Alberta and for the American jurisdiction. We used the data provided in Lashar et al., horn size adjusted to age 7. So we ignored the bias that tends to make it less likely to pick up declines. And we used the data they provided controlling for environmental effects, which was a very good idea. Now, in Alberta, the overall slope is negative. The confidence interval of the slope do not overlap 0, and the predictions there is a decline about 93% of the units. In the States, the slope is also negative, but the confidence interval overlaps 0, and the predicted proportion negative slope is just over half. So this is actually something that is fairly consistent with probably overall there is no change, although it may be worth having a look at these areas that are declining. So really what this paper shows is that there is a substantial difference between Alberta, where the hunt is essentially an over-the-counter hunt, there is no quota, and there is a long hunting season, and what's happening in most of the jurisdictions in the States, where the hunt is much more conservative. So what the paper shows actually is it reinforces the conclusion that the decline we're seeing in Alberta is actually due to hunting and use evolution. So to conclude, I think overall this evidence clearly demonstrates that if selective hunting is intense, legislated or dictated by preferences, and it's like that for decades over a large area, the horns of mountain sheep will evolutionarily shrink. This is easily fixed. And I think that really where we need to bring the debate is not so much is this happening, is not happening, it's clearly happening, how do we fix it? And the last paper that I talked about, the Lashar, clearly showed that you can fix it, you can avoid an evolutionary change by using evolutionary light management, which is essentially lowering the selective pressure that comes in with the hunt. So thank you for your attention. These are all the people that contributed to this work and agencies that financed, and I'll take any questions if there's any.
If anyone has any questions, there's the Q&A option at the bottom of your page. Thank you, Marco.
Okay.